a lot of what we do involves A/B testing, looking at two or more variations of a single idea. So if I want to know whether or not a particular medication decreases blood pressure, or if a tutorial in person causes better grades than a tutorial online, or if a coupon actually affected sales. So I look at sales one week and then I look at the sales in the second week, and the coupon was issued in between. The first group didn't have the coupon, the second group did. I can then say, hey, did this have an effect? I can go so far as to say, oh, I just took two different samples from the same group. Maybe my sample variation was big enough that I need to know whether or not those were different from each other. Even if I draw from two different populations, I can do some comparisons here. But I'm doing the same hypothesis test idea. I want to know whether or not my assumption, my null hypothesis, is true. So we're going to have to figure out what our null hypothesis and our test statistic is going to be for any given setup here. And again, like with our one sample tests, these come in a couple of flavors. Our first version talks about comparing the means from our two groups. And our samples are independent of one another. So what I'm really asking is, are these two means different or are they the same? Is one bigger? Is one smaller? I'm going to be able to have our same three versions, left, two tail, and right tail, based on whether I look at the difference of these two means. So I have mean 1 and mean 2, whether they're from two different populations or from two samples within a population, that's okay. And I think there should be some known difference between these two. For example, you get told, take this medication, it'll lower your blood pressure by at least 20 points. Then I'd want to know that the difference would be at least 20, right? So there's got to be some change between them. I'm going to call that benchmark difference D0. In the example I just gave, that difference was 20. But I could say, hey, I issued this coupon on Wednesday. Did it change the sales at the concession stand on the weekend at the football game? Compare last Friday with this Friday and see if the difference is bigger than or equal to 0. So rather frequently, that number is just going to be 0. All right. In a left tail test, let me think about this for a minute. In a left tail test, I would be asking if the difference is substantially negative. So my null hypothesis would be that this difference is big, and my alternate hypothesis would be small. See how my alternate hypothesis is the left end being negative? A two tail is either equal or not, and a right tail simply reverses these two inequalities. So I'm going to need to compute some sort of statistic and compare it. With my benchmark. I need a thing to compute, a test statistic. Okay, wait a minute. If I'm comparing mean, I was just doing one mean, what was my test statistic last chapter? What did I use on Wednesday or on Monday? That's the thing I calculate to make my decision, but that included my test statistic, the thing I was checking in that calculated value. When that's the result I got one way or the other. I need to know what I compare to this benchmark. So in the Z and T calculation, I took the expected thing and subtracted it from what? That is my benchmark, the expected, that's the D0. The calculated thing included that piece. Look at the Z-calc formula. Mike, what's the top of that Z-calc formula?
Just be just X bar minus
My benchmark, right?
yeah.
So the X bar minus the benchmark. I need the X bar. I don't have anything to calculate, right? I have the mu1 minus mu2. That's the benchmark. So I need to know what this is to try and write this out. In our case, because we're doing two of them, I'm going to have sample means, just like I did before. But this time, instead of just one of them, I've got the two of them. I'm looking at this difference. Now I got to figure out what the Z-calc thing is, right? But I can, or the T-calc. How do I know which one to use?
Didn't say that they're both from a sample, so it'd be the T.
That wasn't the way we decided on T or Z in the last chapter.
Well, if they're from a sample, then I'm assuming you don't know the population.
That's going to be my discerning factor, right? Do I know the population standard deviations? Bingo. And then there's even a subfactor in here because these are two different variations, right? So there's a possibility. Depending on whether those variances are equal or different. So I actually have to make a little bit more of some knowledge checks to like, okay, what things do I know? What things do I not know? Now, that population variance, if that's known, I'm going to want a z-score. But I did say something up at the beginning of this description back here that I haven't really figured out what that means. What was our definition of independent when we were talking about probability? That's all the way back in chapter 5. What did independent mean? Two events were independent if. Okay, if they can occur at the same time, that means they're not exclusive to one another, right? But independent meant a little bit more than that. The question on the exam about the departure times for the flights, right? Trans-Pacific flight and late or something like that. I don't remember what the two pieces were in the question.
So it's like, I think if one influences the other, it's not independent.
Exactly. If knowing one changes the probability of the other. If knowing that the flight is trans-Pacific means it's more likely to be late or less likely to be late, makes a difference. So independent here means influencing, not influencing each other. So when I think about independent samples, my choice of sample over here in group 1 has no effect on my choice of sample in group 2. So I think of these as like I did two completely separate sampling procedures. All right. I'm telling you right now, turn to page 368, 369 in the text. There are 3 fairly large formulas in boxes, and it's all summarized in the middle of page 369, and it looks nasty. You should put a post-it flag here. You should put a mark next to this on page 369. These are the formulas we're going to use. But then I'm going to show you how to do it on a computer. Because 99.9% of the time, we're not doing this crap by hand. So, 3 options. Do I know the standard deviations? Option 1. If I know sigma 1 and sigma 2, I want a z. And then I'm going to say that my calculated z is to take my test statistic and subtract my benchmark. What do I divide by? In the formulas we were using last time. What do I normally divide by down there? Y'all should be looking at the formula sheet you're already beginning to write for the next exam and put all these formula things on it, which is the standard deviation divided by the number of things, right? But this time I've got two of them, right? I've got two standard deviations. So I'm going to use both of them. Sigma 1 squared over n, 1, and sigma 2 squared over n2, and I'm going to take the square root of that together. Now notice, this is something different. I use s over square root of n, right? For our margin of error stuff, I use the standard deviation and divide it by the square root of n. But if I thought of taking the standard deviation squared, dividing by n first and then taking the square root, that would be the same thing. But because I've got two standard deviations and two populations, I need to treat each of them separate. But I want their combined standard error, not the standard error on each one. I want to combine that standard error. This is going to make my numbers smaller. That'll make that bottom bigger. And then I'll use my normal distribution. And I'll say, oh, am I in the reject or accept area? And I'll figure out what my test is. Or I can calculate my p-value. Now, I wanted to do an example of this. And I looked at the textbook. And there weren't any. This pissed me off. Why would you list this formula first and then have no examples? And none of the questions in the book actually use this formula. You know why? Because it's really, really, really hard to know the standard deviations in advance. So I cheated and I found a problem that did this. I went to a website, the Center for Innovation in Mathematics Teaching, and I wrote up one of their examples. They're going to go out and do an environmental impact survey. The alkalinity of the water in the upper reaches of a region is normally distributed, standard deviation 10 milligrams per liter. At the lower part of the river, it's 25 milligrams per liter. Per liter. That's the piece of information that I need to have sigma 1 and sigma 2. There we go. I'll call the upriver 1 and downriver 2, and then I can actually go. This is printed in our in-class examples section on our Canvas page. You've got this PDF available to you. And then they do the readings. And here's all our data. So here's the question. Are the lower part of the river more alkaline than the upper part of the river? Let's say there's a chemical factory in the middle. Is it doing stuff and dumping it in the river? Is it changing the pH of the river? Now, alkaline water, basic, feels slippery. It's harder to wash with. It's actually a problem if you want to use that water in some cases. So knowing whether or not the pH changes in one region or the other matters. Notice they didn't do the same number of readings. Only 10 readings in the upper part, but 15 in the lower part. So I have different population sizes, different ends. I want to know if the water in the lower reaches has greater alkalinity than the water in the upper reaches. So I said, okay, apparently I made 1 the lower and 2 the upper. And I want to know if the water in the lower reaches is bigger, so the alternate about this is mu1 is bigger than mu2. If that's my alternate, that's a right tail test. The other way to say is that mu1 minus mu2 is bigger than my difference. And that's how I see that to the right end. Look at the positive side. Oh, okay, that means I'm going to use exactly this calculated formula. And I ran through the numbers. Now, I didn't do a p-value, but I got this number, 2.574. Let's just call it 2.57. What's the p-value that goes with 2.57? Normal distribution, that means I can use table C. And if I'm using positive 2.57, 2.5, 0, 1, 2, 3, 4, 5, 6, 7. 0.9949. What was the number we had? 1%, right? If that's my area, what's the p-value? What's the reject region up there in the corner? Which is smaller than 0.01. And I reject when my p-value is small. Out it goes. P-value is too small. Bye-bye. Which means there is something changing the alkalinity. Questions? If I had to work this hard to find this example, it's unlikely that in a business setting, we're going to know our standard deviations. So this is an unlikely to get used formula. But it was the first one in this section. I kind of went, okay, let's do one of these. What the hell? You don't have one? Why would you do this to me? So what's more likely? I don't know either of my standard deviations. I have to use the sample ones, right? If I have to use the sample deviations, then I want a T. But here's where the additional question comes into play. If I don't know the standard deviation, it is possible that the variance in one group will be different than the variance in the other group. It is possible that they're the same, but it's possible that the variance is different. For example, in the example we were just looking at with the water, the standard deviation upstream was known to be different than the standard deviation downstream. But if I'm taking samples from the same population, I'm going to take a sample of students in anatomy and physiology, which is a fairly large course. I'm going to take 10 students who have an online homework system. I'm going to take 10 students who have a pencil and paper homework system, and I'm going to compare their scores on the next exam. Does doing an online homework give you better exam results, or does doing a pencil and paper homework? Well, I would need to know the standard deviations. I have no idea. But if they're in the same class, I could make the assumption that the standard deviations are the same. If the standard deviations are the same, then I can combine them. if I assume that they are equal, then I can create what's called a pooled variance. Which I'll call sigma p, pooled. Now, variance is, oh, sorry, not sigma, S. SP. Now, this is a weighted behavior. Because again, my populations might not be the same. I talked about taking 10 students with paper homework and 10 students with online homework. But as we saw in the river example, it could be 10 in one group, 15 in the other. So I need to weight SP, which means I need to calculate this differently. What is this? Ah, what? If there were fewer people in group one, I would want that variance to count a little less. If there were fewer people in group two, I'd want that variance to count a little less. So if I multiply the variance for each group by the number of people, why am I subtracting one? We've seen subtracting one bullshit before. Why am I subtracting one? This is actually all the way back in chapter 4 in our descriptive statistics pile. I did something where I subtracted one from the number of people.
Like, wasn't it something with binomial, I think?
Even before that.
Yeah.
When we just figured out the formula for a standard deviation, it was either the square root of n or the square root of n minus 1. And it was n minus 1 when we did samples. So this n minus 1 is in here to adjust for the fact that I'm using samples and to spread it out a little wider just in case I don't have a good sample. But I have to find n1 minus 1 and n2 minus 1. Wait a minute, if I subtracted 1 from each of the populations, that's the minus 2 on the bottom. So I take 1 out to account for the fact that I am sampling. And if that's what I'm doing with my population, with my sample sizes, that's going to change the degrees of freedom. Because degrees of freedom was number of people minus 1, wasn't it? Well, now it's the number of people minus 1 each time. So my degrees of freedom is that same number that I've got on the bottom. If I do this, my T calculation is the same as my Z calculation. Now, what went on the bottom here was variance over the number. So I'm going to take this variance, the pooled variance, each time. Oh, guacamole. Now, again, I'm the kind of person who wants to see this stuff done, and then we'll run it in the computer. So let's start with this first problem's idea. I have two randomly selected college majors. And I go, two randomly selected classes. I look at the juniors, I look at the seniors. I take a sample, and I notice that out of N1, 15 juniors, I have an average GPA of 3.05 and a standard deviation of 0.2. Out of 15 seniors, I have a standard deviation of 3.25 and an average of 3.25 and a standard deviation of 0.3. And they tell me to use alpha's 0.025, 2.5%. And this is a left tail. So I want to know if the grades went up or down. So let me write down what I've got, and we'll go from there. 10.1, problem A. X1 bar is 3.05. The standard deviation for this first group was 0. Come on, just 20. And there were 15 of these. X2 bar was 3.25. My standard deviation was 0.30, and there were 15 of these people. Alpha is 0.025, and it says left tail test. So the first thing I want you to write out for me, what's the null hypothesis? What's the alternate hypothesis? We wrote these down earlier. If I'm doing a left tail test, that's what my null and alternate look like. I want to know the alternate is that it went down. If I assume the variances are equal, I can pool the variances. So let's figure out SP squared. That's that big ugly formula we were just looking at. Put in all the right numbers. How many people in population 1? So 15 minus 1 is 14 times 0.2. There are also 15 people in population 2, 0.3 over 15 plus 15 minus 2. My denominator is 28. What's my numerator? Oh, hang on a second. I forgot something. What did I forget? Right here in this line. Yeah, because it's S1 squared and S2 squared. Doesn't help if I forget square things. Okay. What do we get here? 14 times 0.2 squared plus 14 times 0.3 squared. 1.82 divide by 28, and I get 0.065. Now, I want to do my t calculation, right? I also need one other piece of information. I need a t critical. I'll get that afterwards. So I'll put that over here in a box so I can remember to do it later. T calculated. T calculated is x1 minus x2 bar minus my expected difference over SP squared over N1 plus SP squared over N2. That's why I didn't bother to take the square root. I just left it as SP squared because I only ever use it as SP squared. So, what was average 1? Average 2 was 3.25, right? And I said, did they go down? I was comparing it to 0. And now, 0.065 squared over 15 plus 0.065, no, that's not squared, we already squared it, over 15. I get negative 0.2 over 0.65 over 15 times 2 square root 0.093094, lots of other decimals. And when I divide, what do you get? Now, doing a t-test, I need my t-table. So I grab my t-table, which is in here somewhere. Here it is, t-table. Oh, wait a second. In order to do a t-table, I need degrees of freedom. What's my degrees of freedom? Careful. Degrees of freedom is total population minus 2, 28. It's the same as the denominator in our pooled variance calculation. So up here, DF is 28. Now, I go to the 28 line, and I wanted 0.025 for a one tail. That's the third column. 1, 2, 3, 2.048. Do I reject or not? There's something I need to do to my calculated t-value to figure out whether or not I should reject. Or there's something I need to do to my critical t-value to figure out whether or not I need to reject. Because I'm doing a left test. I either make this number negative or I make this number positive. You either take the absolute value of your calculated thing, or because you're doing a left test, you look at the negative of the critical value. One of the two. Hey, wait a minute. We're outside, aren't we? In this one, hey, you're definitely too small. In this one, hey, you're too big. What does that mean? We reject. And that means this alternate hypothesis is true, and mu1 minus mu2 is less than 0, or mu1 is less than mu2, which means the grades went down, or the grades in group 1 are lower than the grades in group 2. But when I go back and I look at the text of the problem starts to piss me off, because they didn't tell me which group were the juniors and which group were the seniors. Would have been nice if they had, but they didn't. So I don't know. Are the seniors doing worse off than the juniors? Are the juniors doing worse off than the seniors based on these GPAs? I know group 1 is doing worse than group 2. Now I have to go back to the person who did the survey, but which group is which? And this is where being a statistician is a benefit, because I am blind to the groups. I don't let that influence my decision. I don't know which group is juniors and which group is seniors. But my assumption would be that seniors would have slightly worse GPAs for two very different reasons. They've taken harder classes in their senior year, and people get senioritis and get bored in the middle of the spring. So, but that would be an assumption. Since I don't know which group is which, I have no way of letting that influence my decision. Now, I created this spreadsheet. You'll notice in that middle column, question 1, part A, there are my numbers: 3.05, 0.2, 15 people. 3.25, 0.3, 15 people. Wait, I forgot. I want this in the recording. There. And then I said, we want to do, what's the assumed difference? I left that blank because I said the assumed difference was 0. And then I said, okay, degrees of freedom is number of people in group 1 plus number of people in group 2 minus 2. I did the variance calculation. There's the formula for it right up there. The same formula we had written down. Alpha was 0.02. I wanted a left tail test. See how that's a drop down? You can pick whether you want to do a left, a 2, or a right tail test. It looked up the calculated t-value, found, hey, wait a minute, look, t inverse. I can do a t inverse. That's how I can get the t-value off of here or off of Excel rather than looking at the table. And then I said, what's the p-value for that? 0.020. And what was our alpha? 0.025. We reject. Again, this is in our available spreadsheet. But notice there's a third column here. Third column says unknown population variances assumed different. This version made the assumption that the population variance sigma 1 and sigma 2 were equal. That's why we were allowed to pool the variance. That's not always true. I'll come back to that in a second. If I can't assume that the population's standard deviations are equal, or if I don't know that, then I can't pool. And if I can't pool, I'm going to have to use S1 and S2 separately. But this is going to give me a slightly more conservative estimate. Because of that, when I do my T calculation, I don't have a pooled variance. So I get S1 squared over N1, and I get S2 squared over N2. That's the same stuff. But now, in order to deal with the fact that this is going to be a little bit more conservative, I need to change the degrees of freedom. This is due to two statisticians by the name of Behrens and Fisher, and a guy by the name of Welch who came along and said, here, this will make it better. So Welch says we change DF. The way we figure out the new DF sucks. Those should actually be separate fractions. So I need to erase something there in the middle. Let me get my correction tape. Those should be separate fractions. Oh my God. So I'm going to shove this into a calculator, and whatever I get here, I'm going to round up. Now, again, this is a calculation I don't want to do by hand. And that's what we see in this third column here. A change to the degrees of freedom. Big, ugly calculation there. I end up with 24 instead of 28. Oh, wait a minute. No, it's not rounded up. It's rounded down. Round this down, not up. As I look at the formula up there that says floor, floor needs to go down, not up. All right. I did all of that first problem. This is part A, part B, and part C. And that's an available to you download. But we don't have to use this particular spreadsheet. Some of these are built in. We'll do them that way when we have the data as opposed to having the summary statistics. And that's what we'll look at on Monday. We'll see you all then. Have a wonderful weekend. Remember, your homework for chapter 8 is due on Monday. 8, 9, your homework for chapter 9